Hi everyone, welcome to the final session of today in the MLDS track. And our speaker is Neha Gupta, and the title of her talk is Dameflame, a Python library for interpretable matching for causal inference. Neha?
Hi, is everything looking good?
Yes.
Okay, cool. Thank you all for coming to this talk and listening to me chat about this Python library and causal inference generally. And thank you to SciPy for allowing us to talk about this. So I am presenting this as part of a large lab group at Duke. We do everything from package development to more like the actual development of the algorithms as well. And we do all our front end and all our testing as well. So if you have any questions about any of that, you're welcome to reach out via our GitHub issue tracker or via email. I will get to talking about this package in the third part of this talk. And for the first two parts of this talk, I will discuss causal inference and matching within causal inference for kind of a broad, general beginning data science audience, but I hope that the last part of the talk will be interesting to advanced causal inference practitioners as well. So just to begin by defining causal inference, we are generally trying to draw conclusions that something is being caused by something else. And these types of questions can be applicable across many fields when people are wondering what will happen if they prescribe drugs to people, what will happen if they make a certain policy, or what will happen if they raise prices. The goal is to be able to answer these kinds of questions quantitatively using statistical methods and domain knowledge. I'm going to be talking about cases in which we use observational data, meaning you can only observe one outcome per individual. And I want to clarify that this is different than prediction tasks because we have observed one outcome for each individual already. One example you can carry with you as I talk about causal inference is the example of giving somebody a pain reliever medicine. It is kind of hard to say whether the pain reliever medicine is specifically what caused somebody to feel better if they had a headache, when we don't know what would have happened over that same period had they not taken the pain medicine. Maybe they would have felt better anyways. Because they took it, they are in the treatment group, and had they not taken it, they would be in the control group. To introduce a little bit of notation that I will come back to as I proceed talking, we are going to aim to quantify the effect of treatment, which in these cases will be a binary treatment, and we're trying to quantify the effect of that treatment on outcome, which we will denote as Y, and it is in the presence of covariates X. Covariates are any observed characteristics or features that you think are relevant. So in the example of pain medication, that may be some physical attributes about your person. Each unit in a data set can be denoted as I, and each unit has two potential outcomes, yi1 if they did do the treatment, and yi0 if they did not do the treatment. If a unit did the treatment, then we do not actually see yi0, and that one is what we call the counterfactual outcome. So the question of causality is comparing actual outcomes to counterfactual outcomes. What would have happened had things been different? When we're able to estimate counterfactuals, we use these to estimate treatment effects through metrics like the conditional average treatment effect, which we denote as CATE. Another interesting estimator to us is the average treatment effect, ATE, which we denote as the estimated impact of a treatment for all individuals. And so that's the yi minus y0. In order for these estimators to be valid, you need to be able to believe that all covariates have been observed and exist in your data set. Otherwise, your estimators might not be very good. As an example of that, if we're looking at, for example, a job training program, and we're interested in measuring whether the people who participated in the program have increased wages after the program, then it's important that we measure a lot of other characteristics of the people who did and did not participate in the program. Do we know things like what their educational background is? The reliability of causal inference and causal inference estimators is dependent on the credibility of your data and accurate data measurement. You need to be able to believe that you measured all relevant variables. And sometimes it may not be possible for a particular policy question to be answered with a given data set. So it's just important that we're able to be sure that the job training program increased wages. And it's not the fact that everyone who did the program also received a college degree, for example. With that, I guess I will close on talking about causal inference and start talking more about specifically matching within causal inference. Many methods and statistical options exist for people who are interested in causal inference. You might consider instrumental variables or difference in difference. Your choice to use matching or not use matching really depends on your data set and your specific problem. And ideally, it would be cool if you're able to use multiple tools. You've already probably noticed some prerequisites to matching. I mentioned that you need to have an observed outcome for each unit and that you need to have observational covariates. So you need a Y and an X. And some other important prerequisites exist that I'll talk about now. One is the SciPy requirement, which is that treatments applied to one unit can't affect the outcome of another unit, and units in your data set can't interfere with one another. So you don't want one unit to be causing a headache for another unit if you're doing a study on headache medicines. Another important one that I already mentioned is unconfoundedness, ignorability, and avoiding omitted variable biases. A last one is overlap of treatment and control, and we need the units that are in the treatment study and the units that are in the control group to be able to be similar across covariates. I think that I will now begin by talking about what matching really is, first starting with the ideal case, which is exact matching. So when you're doing exact matching, you are estimating causal effects on observational settings, and one ideal approach would actually be if you can match every treatment unit to an exactly identical control unit. So if you were able to find two people who are sharing every physical attribute and had the exact same symptoms prior to when only one took the pain reliever, you can just see how their outcomes differed. So that would just mean that all their covariates are the same, meaning that for unit I and unit K, xi equals xk, and then we can say that unit K is an exact match for unit I. To see the differences in their outcome, you can just subtract the yi from the yk, and that will be your estimator there. The problem is that this ideal case isn't always possible. For high-dimensional large data sets, very few identical twins exist. So then instead, we are trying to find situations in which xi is just close to xk, or two units are similar across many covariates, but not exactly identical. So the question of deciding what two close units are is where the question of choosing a good matching method comes in. There are many different matching methods that will define close units differently. And for this Dameflame Python package, I'm going to describe to you how we define finding close units to match. And I will spend the bulk of my time on that. But before I do that, I'll quickly introduce to you two other common matching algorithms and packages. One of them is the propensity score matching algorithm. Propensity score matching offers a variety of distance metric options, but it begins by reducing a dataset down to one dimension and using distance metrics from there. This is really popularly used in the R package Matchit, which if, of course, as we are Python users, you would want to use the rpy2 package to plug in an R package. You would also have to use the rzellig package to find the treatment effect estimators. Two other options that exist are PyMatch and DoY. Those two are inherently in Python, so you wouldn't need to use rpy2. So those options are also there for you. Another common algorithm is coarsened exact matching, or CEM. The way that CEM finds close matches within a data set is that it essentially just coarsens covariates or asks users to manually do so. This is most popular again in an R package with RCEM, and then it's also been recently added to RMatchIt. So you would have to use RPy2 for those. When you're deciding between matching algorithms to use, whether that's propensity score, CEM, DameFlame, or something else, some of the considerations you'll be interested in is whether you're able to get good estimators and high quality matches from that matching package, which I already talked about. Another consideration that you might have when choosing a matching algorithm is whether your matching algorithm will give you interpretability and whether you can see why 2 units were matched and which covariates influence the choice to match those covariates. Details that compare the DameFlame package to CEM and propensity score are available in some of my team's other publications, and we offer a comparison of the accuracy of those estimators on simulated data sets. So I will reference you to that if you are interested in more details comparing matching packages. But for the rest of this time, I think I will proceed to talk about the DameFlame Python package at this point. I'll start by defining it. So the Flame package, the DameFlame algorithm the DameFlame package offers 2 algorithms. One is Flame and one is Dame. The Flame algorithm stands for fast, large-scale, almost matching exactly, and the Dame algorithm stands for dynamic, almost matching exactly. Flame runs on a bit vector computation for backwards feature elimination, and Dame uses a downwards closure property. I want to make sure I highlight that both of them are only for discrete observational covariates, and at this time, they're only for binary treatment. Continuous outcomes are more than okay for sure. I will walk through an example of the Flame algorithm now. So let's consider a data set in which gray is the treated units and orange is the control units. And again, remember that our data set has categorical covariates to match on. So the package DameFlame requires users to provide a holdout training data set in order to determine the covariate weights. If a user doesn't provide a holdout training set, then the input data will be automatically split into matching and training. Once you have those 2 split, then in order to start generating match groups, the package is going to proceed by iteratively dropping covariates, and it matches at each iteration. So let's suppose we have 20 covariates labeled X1 through X20, and in this hypothetical scenario, we already know the feature importance, and they have already been labeled from most important to least importance. That's not a necessity for this package, though. That's just for the sake of this illustration. So the way that Flame works is that on iteration 1, it will match units exactly on the entire set of covariates. So it will find all exact identical twins, as I mentioned, the ideal case, and those will be placed into a main match group. Each unit will have at most 1 main match group, and for this demonstration, though, we will match with replacement. You also have the option of matching without replacement in the package, but when you match with replacement, units can be placed into additional auxiliary match groups, so they'll just be put back into the matching data set once they've already been matched. So Flame uses a backwards feature elimination method, where at each iteration, it removes the least important covariate set by using machine learning on the training data set to find the least important covariate set. So it balances the choice of the most important covariate set for predicting outcome, along with the choice of the covariate that matches the most units, which we call match quality. So when it first decides to drop covariate X20, on that iteration, we will match units on covariates X1 through X19. So supposing 2 units have been matched on iteration number 2, in which X20 was dropped, they have then been matched, meaning that they have the exact same value for covariate X1 through X19, but covariate X20, their eye color, is a value that was determined to be unimportant by the algorithm. So they can have differing eye colors, but the same value for everything else. So they've been placed in a matched group, and the algorithm has prioritized important covariates without matching on unimportant ones. Flame continues this process and eliminates 1 covariate at a time until the remaining covariates are no longer useful for accurately predicting outcomes on training sets. It's able to stop wherever a user feels is important, and I'll talk more about stopping criteria in a few minutes. Looking at the DAME algorithm, the DAME algorithm operates similarly to Flame, except it uses downwards closure properties to eliminate the least important subset of covariates at each iteration. The first iteration will again always be an attempt to match units exactly. Next, it drops subsets until the remaining subsets are no longer useful to us. So that means that it iterates way more times than Flame, and it considers way more covariate sets for matching. So it's much slower, but it produces higher quality matches. Another option you have within the DAME-Flame package is to run a hybrid Flame-DAME algorithm by using Flame to first quickly remove irrelevant covariates and then switching to DAME. I will now run through a quick start example of the API and then dive into talking about some of the advanced features and considerations of the package, which I'll show you in the documentation as well. These are all the features that I'm going to talk about soon. One that is also important to highlight is that we have a forthcoming large-scale database version, which will run on a PostgreSQL backend. That will be able to help users scale things larger. Currently, it just runs on a pandas data frame that can be input, so it's contingent on your compute processing abilities. You can install it via the version that's on SciPy or the version that is on Git. We try to do everything we can to make sure that the thing that's on Git is stable and building. So hopefully you shouldn't have any issues with either one. The Git one will be more up to date. So I'm going to talk you through a quick start example. You can also see this in the documentation. So for my quick start example, I'm giving you a super tiny 4-unit data set. You import DameFlame, import pandas to have your input data frame. So this is our input data frame right here, super, super tiny. You want to start by declaring a matching object. Specifically, I'm going to run the DAME algorithm, so I'm declaring an object of type DAME. Then on my object, which is named model, I'll first call the fit function and I'll pass in my holdout training data set. Then I'll call the predict function and I'll pass in the matching data set. The algorithm by default has a variety of verbose output options, which you can use to view the results of the matching as the algorithm proceeds. The default output is a data frame, which will have all the matched units and all the covariates they were matched on, with stars denoting covariates that were not used to be matched. You can also additionally, for output, see the matched groups and the units that belong to each matched group. So here we can see that unit 0 and 1 have been placed in a matched group together. And from here, we can see that unit 0 was matched on covariates x2 through x4 along with unit 1. I will now close this window and move to the documentation window. So let me change the screen share for a second. Okay, so I assume everything is good. Someone please stop me if it's not. So here we have all of the advanced options that I discussed earlier. I will walk us through the most important ones now, but of course this is our public documentation. It's linked on the GitHub repo, so you can definitely find this and find the relevant information as you proceed. So when you declare a flame or a DAME object to do your matching on, I have all of your advanced control parameters listed here in the documentation, and the documentation proceeds to provide the default and a description of each parameter as well if you scroll down. Some important ones to highlight is that this adaptive weights parameter provides you with the option to change the machine learning algorithm, which is where the machine learning algorithm that is used in selecting the most important covariates can be adjusted. So the default machine learning parameter, the machine learning algorithm, is the ridge regression, and the default alpha for our ridge regression is 0.1. Another important parameter to change that you can change if you want is matching with or without replacement. That can be toggled here via the repeats parameter. There's two large other groups to mention. One is the parameters that are used for early stopping criteria. As the flame and DAME algorithms proceed, subsequent iterations match with lower quality, so users may want to stop the algorithm before allowing it to run to completion. You might want to stop after a particular number of iterations, or you might want to stop after a proportion of unmatched control units or a proportion of unmatched treated units. Another large group of options is the missing data handling options. The missing data handling options exist in case a user has a data set in which not all covariates have been observed for every single unit. Because these are so many parameters for missing data and for early stopping criteria, we go into a further discussion of those within the user guide. So users can click on the user guide in order to see a discussion of, for example, in the case of early stopping, each of the parameters, technical details, as well as a usage recommendation. Hopefully you find this guide helpful as you're deciding when to stop your algorithm. The same details exist for missing data handling, as I mentioned. We offer the MICE option, which is multiple imputation with chained equations. We also offer the chance to skip matching on missing units or skip matching on only missing covariates, but continue matching on those units. We have further statistical definitions for the treatment effects. And one additional note within the API is that after somebody has run the DAME or FLAME algorithm, in order to get the treatment effects, they can select any post-processing. Again, I describe all the parameters for the post-processing functions and have quick examples for each of those. For more detailed examples, users can click on the Examples tab. We have 4 examples here that run on simulated data and 1 example that runs on a real data set. For each of the examples, we have a fully reproducible code and a downloadable notebook, along with a discussion of what the experiment is doing. Each of the examples has some form of a plot as well, because my aim is that users can be able to download this code, run it with your own data set, and then use my plotting code to create a plot for your data set. In this example, I show the ability of DAME FLAME to allow users to interpret covariate importance, because I have a plot in which I compare each covariate across the number of units that were matched on covariates. So therefore, in this example, we can suppose that covariate named X0 had very many more units matched using that covariate than covariate X4 did. Therefore, covariate X0 could be interpreted to be more important than covariate X4. So all of this documentation is available online, and we're always happy to expand it or take suggestions on that as well, as this is a fully open source package. I think that is everything major that I wanted to show in the documentation. I guess to close out, I will flip back to my PowerPoint quickly. And last thing is that for development details of our package, as that is important to this group, we did what we can to make sure that the package has very minimal and only common dependencies. So we rely on scikit-learn, pandas, and NumPy. The upcoming database version will rely on PostgreSQL as well. Our test suite is something we're happy with at this time, always open to suggestions though. We used Travis CI and coveralls to get a high code coverage percentage. In order for accuracy of the algorithm, we also tested it against a separate package written in R with a separate backend, which is called rFlame, offers the Flame and Dame algorithm just in R. And for code style, we used PEP8 and ran it on Pylint to show that, at least where we agreed with it. And code and good documentation is really important to our team, so definitely reach out if you have questions, contributions, or any bug reports at any point. So I guess with that, I will close and see if we have any questions at this time.
Thank you so much for this great talk, Neha. We have a few minutes left and we have a couple questions. One of the questions asks, is there an associated paper, peer-reviewed paper available with the documentation?
We don't have a peer-reviewed paper for the package. We have a peer-reviewed paper for the algorithms. Those are something I can link to you here. Am I still screen sharing? I am not. I will provide those, and then
okay.
Let's see. Why does the holdout matter? What would be the consequence of using matching data for training? I think that it is really up to the user. I think that using a separate holdout data set as a small sample definitely allows the algorithm to run faster. You could run it on the entire matching data set if you wanted. Presumably that would be slow and you could lead to some overfit errors there as well. Definitely something that would be open to experimentation for users. Are there any other questions? I will find the peer-reviewed papers.
If there are any other questions, please post them on the Q&A tab. There it is. Okay, we have a question. I missed a discussion about what variable types are usable. This currently works on both binary and continuous, but not categorical.
So, the covariates need to be categorical. They need to be binary or categorical, meaning like 0, 1, 2. Continuous is not acceptable right now, meaning like 2.1, 2.2, 2.23, that kind of thing. For those, I would recommend you use some other packages other than Dameflame.
All right, with that, we are out of our time. Thank you so much, Neha, for this great talk and introducing Dameflame to us. And thank you everyone for joining the session. Next up in the schedule is lightning talks, and hope to see you all there. Enjoy the rest of the conference.
Thank you.
Thank you.